Good afternoon. Red Cross Science teacher Scott Johnson here, wanting to bring you today's motion and forces lesson. Today we're going to look at Newton's second law of motion, which actually has a formula that goes like this: F equals m multiplied by a. Now at first you might go, okay, well that really doesn't mean anything to me, but here's what it actually translates to. An object's force is equal to its mass times its acceleration. Now, in order to understand that, we need to understand a few principles about this. First, let's break down the components of force. Okay, first off, you have mass. Now, if you will recall from earlier discussions we had this year, mass is actually the amount of matter that an object contains. Okay, the more matter something contains, the more mass it has. In other words, the more molecules it has. Okay, the more molecules, the more cells, then the bigger the object is, the heavier it is, the more mass it contains. You could say that I have way more mass than this wooden spoon. This ball has more mass than this little block, right? So mass is how much matter an object contains. And usually the larger an object is, the more matter it contains. But there are exceptions, and we're going to look at one of those during this lesson. Now, you take that mass and you multiply it by an acceleration. And acceleration is a force. It's a movement, right? The more energy you give something, the more it accelerates. When you think about it in terms of a car, if you step on the gas, the car accelerates. In other words, the more gas you give the car, the more acceleration you're going to have. So when you think about a car, they're rather heavy, right? They have a lot of mass. There's a lot to them, especially as they get bigger. You have cars, you have trucks, you have semis. Think about airplanes and boats, right? So you take that mass and then you multiply it by the acceleration. Well, those two things multiplied together create the total force that an object has as it moves. So the larger something is, multiplied by the faster it moves, creates more force. Think about this wiffle ball. This wiffle ball is plastic and it's completely empty. It's hollow. It's very light, right? I wouldn't go to a bowling alley and try to roll this down the lane to try to knock down pins. You could imagine, well, number one, I'm a terrible bowler. So if I tried to roll this down the lane, odds are I'd go in the gutter or probably another 2 or 3 lanes over. But I would be willing to bet, too, that by rolling this, not by trying to throw it or anything like that, I would bet that by rolling this, because of the friction as it slides and rolls across the wood of the lane, it's going to have a hard time making it all the way down to the pins because it contains a lot less mass. And then, once it gets there, this probably isn't going to have near the force. It's mass times its acceleration, right? It's probably not going to have enough force to even knock the pins over. However, if I take an actual bowling ball, something that weighs 8 pounds, 10 pounds, 15 pounds, 16 pounds, and I even roll that just a little bit, if I don't get it in the gutter, even a slow roll will allow it, once it gets to that pin, it's still going to have enough acceleration multiplied by its mass to create enough force to knock the pins over. And that's what Newton's second law is all about. F equals m times a. Your force is equal to the mass multiplied by the acceleration. Let's say it one more time. An object's force is equal to its mass times acceleration. Think about football. If a kid is coming through and they're running with the ball, and I've got 2 guys coming at me that are trying to tackle me, right? If one guy is pretty small and doesn't weigh much, and the other guy is like 6 foot 300 pounds, I'm going to run away from the bigger guy. In fact, I'm going to run to the smaller one. You might say, well, don't run towards one. He's trying to tackle you. Yeah, but if I think about acceleration and I think about mass and then multiplying those together to hit me and with enough force to knock me down, I know that this little guy over here is going to have to run a whole lot faster to create that kind of force. This guy's not going to have to create as much because he has a great deal more mass. And we can see this in several things. First off, think about cars. When the car accelerates, it begins to move forward very quickly. Now, this is where you all need to understand something, and it's kind of a safety part of today's lesson, and we're going to get into this as we move forward. I'm going to grab a marker here. So this car is accelerating forward, and we have the total mass of the car. But with you sitting in the car, you add to that mass. Especially if, let's say, you're in the back seat and someone else is driving the car. You have added the mass of the adult body and the mass of the student body. And so that has increased the mass of the car. You multiply that by the acceleration of the car, and now the car is moving with even more force. Mass times acceleration equals force, right? Now, what makes you sad is that from time to time people get involved in wrecks, and that would involve a massive deceleration. Now, think about that. If acceleration is how fast something is moving, a deceleration is it slowing down. And sometimes it decelerates so much it just stops, right? Especially if you have a front end collision. Now, think about this in these terms. Let's say that you have a car that weighs 2,000 pounds, okay? Let's say you have a car that weighs 2,000 pounds. And let's say that car is moving at 35 miles per hour. Now, some of you sitting at home might go, 35 is not too fast. You're right, yeah. Here in the neighborhood where I live, 35 is the speed limit. You don't want to go over 35. In fact, I would say if you're driving through my neighborhood, I would appreciate it if you go even slower, because if my kids are out front playing, I don't want to have the risk of if one of them were to accidentally go out in the road without looking, you not having enough time to stop, you not having enough time to decelerate, right? To bring your acceleration down. Now think about how much force this car is going to generate if it were to hit something. A 2,000 pound vehicle moving at 35 miles per hour. Well, you guys are awesome at multiplication. All you got to do is multiply that. 2,000 times 30 is going to be 60,000 pounds. And then we add another 5 to that. 2, 4, 6, 8, 10. That means that if this car were to hit something, it's going to hit it with 70,000 pounds of force. 70,000 pounds. Which means that if you're playing in the street and a car hits you at just 35 miles per hour, okay, that it's going to hit you with over 70,000 pounds of force. That's enough to do a great amount of damage to your body, even though most people don't even consider that fast. If you've been in a car before and going 35, you've probably thought, well, this is going really slow. Well, of course, that's why we see slower speeds in neighborhoods. Force is the mass of an object multiplied by acceleration. Could you imagine if we increase this to highway speeds, 55 miles per hour, 65 miles per hour, interstate speeds, 70, 75, 85 miles per hour, still multiplying by the weight and just how much force that creates. That's why it's important when you're in the car to do something that I hope all of you do. And this is my safety thing I want to pitch in there when it comes to Newton's second law. Please, oh please, oh please, wear your seatbelt. I'm going to put a little seatbelt on my guy and my driver here. Some people, they get aggravated about seatbelts, but this is what I want to show you. If this car is moving at 35 miles per hour, guess what? You may feel like you're sitting still in the car, but you're moving at 35 miles per hour too. That's right, okay? Let's say this kid in the back seat weighs 100 pounds, okay? Some of you, 6th graders, you weigh close to 100 pounds. Maybe you weigh just under it. Maybe you weigh just over it. But let's say this kid weighs 100 pounds. Now think about this. Let's say the car, once again, is traveling at 35 miles per hour. And the kid in the back has on a seatbelt. If this car all of a sudden were to decelerate, Okay, we're to massively slow down. Let's say that a deer runs across the road and the driver has to stomp on the brakes to keep from hitting the deer, right? And so the car slows down. And I'd say most of you have been in a car before where the person driving has had to get on the brakes and you feel like you jerk forward, right? That seatbelt is going to help you. It's going to help you decelerate at the same speed as the car. So as long as you have it on, when the car decelerates from 35 to 5, you are going to decelerate from 35 to 5. Here's the problem. I'm going to take the seatbelt off my child in the back seat now. I've had students before in the past that say, I've heard, Mr. Johnson, if you ride in the back seat of the car, you don't have to wear the seatbelt because you're safe back there. Completely untrue. Totally false. Fake news. Don't believe that. And let me show you why. Newton's laws don't care where you sit in that car because the second law applies to you wherever you are. If you're sitting in the back, this is our 100-pound student, moving at 35 miles per hour. And then all of a sudden, the driver hits the brakes, has to decelerate. Your body is still going to move forward at 35 miles per hour. That's right. You may never have thought about it before, but you are moving at the same speed of the car. Even though you feel like you're sitting down, you're still moving at the same speed. So if the car is moving at 35 miles per hour, your body's moving at 35 miles per hour. If the car is moving at 55 miles per hour, your body is moving at 55 miles per hour. If you're on the interstate and the car is moving at 75 miles per hour, your body, whether you're in the front, the back, or even if it's an SUV and you're sitting in the third row, your body's still moving at 75 miles per hour. Well, watch this. If this car is just moving at 35 and they hit the brakes, this child is now going to go forward. And let's say they hit the front seat, okay? They slam into the front seat. They're going to hit that seat with, my eraser. Here we go. You have your 100-pound child accelerating at 35 miles per hour. That means that child is going to hit the seat at 3,500 pounds of force. Many people that have been in back seats before that did not have on seatbelts have experienced whiplash. They have experienced fractures, especially in the rib cage, broken noses, fractures along the jawline, broken teeth, because what happens is they don't think anything of it. We're safe in the back seat. It doesn't matter. Well, and then what happens is when you have this massive deceleration, okay, a massive slowing down, all of this, it's not just the car traveling at this speed, it's the car and everything inside of it, including you. My friends, my awesome students, please wear your seatbelts. Seatbelts were invented solely due to Newton's laws. And which law is that? The second law. Force equals mass times acceleration. An object's force is equal to its acceleration, right? The more mass it has, and the faster it's going, the more force it's going to hit with. Now, I've got a couple of demonstrations here that I want to show you. I like to use things that you can use at home. So first off, I have a bouncy ball, little Barron County basketball, and a wiffle ball. Now, both of these are pretty light, right? Check it out, because I want to show you something. I'm going to drop them both on the count of 3. I've got them equally at the height, so here we go. 1, 2, 3. Notice something? Let's try it again. 1, 2, 3. Everything is pulled on by gravity, which we talked about in our first lesson. Remember, gravity doesn't pull things down, pulls things to a larger mass. Well, gravity doesn't actually care what it's pulling on. Gravity pulls on everything the exact same. So even though this wiffle ball and this bouncy ball are made of different materials and have different weights, they actually hit the table at the exact same time. That's right. If I were to drop both of these off the top of a building onto you, they would hit you at the same time. Okay, check this out. We have a bouncy ball again, and here I have kind of this soft foam Louisville ball. Okay, now both of them really soft, really light. Okay, if I were to drop them on you, you'd be like, I don't care. You'd look up at me and be like, oh, come on, Johnson, don't do that. But the truth of the matter is, even though this one is slightly heavier than this one, they're going to fall at the exact same speed. And that's because gravity doesn't care. It pulls on all of us the exact same. Gravity wants you to come to the largest mass. So gravity wants you to come to Earth. As soon as I drop these, it doesn't say, oh man, give me that one quicker. No, it's all the same. Check it out. Here is a much heavier basketball, right? Little spongy ball, heavier, minier basketball. So check this out. 1, 2, 3. Did you see it? I'll do it one more time. Let's go from even higher. 1, 2, 3. Notice that. Still hitting the table at the same time. If I were to drop a bowling ball and a feather off of the building, guess what? Both would hit the ground at the same time. And do you know why? That's right. Gravity pulls on everything with the same amount of acceleration. Gravity doesn't care. Now, would you rather be hit by the bowling ball or by the feather? Stop it, Tyson. No, you wouldn't want to get hit by the bowling ball. Always somebody out there trying to be smart and funny. You'd rather be hit by the feather. Yeah, but Johnson, if gravity's pulling on everything the same, why does it matter? Well, it matters a whole lot, actually. The bowling ball has a lot more mass, and since the bowling ball has more mass, when it accelerates, it's going to hit you with a lot more force. The feather doesn't have much mass at all. It's not going to be affected by the acceleration because the acceleration, listen, if the bowling ball hits you at 30 miles an hour and the feather hits you at 30 miles an hour, you'll barely feel the feather. You will totally feel the bowling ball, right? And that's all about force equals mass times acceleration. Because the bowling ball has more mass, you multiply it by the same acceleration because gravity's pulling on everything exactly the same. And because of that, you're going to get more force. That's the big thing you need to understand here. Gravity pulls on everything the same. Think about that with a baseball, okay? This baseball, whole lot harder than this spongy ball. Notice I can squeeze. There's no squeezing this, right? If I were to throw this at you at 20 miles an hour, it would hurt. Now, a lot of you out there that play baseball and softball, you might go, yeah, but 20 is not that fast of a pitch. I'd take first base, whatever, Johnson. Right, but you'd rather me throw this at 20 miles per hour than this. Why? Well, this has more mass. Multiply this mass by 20, and it's going to hit you with way more force. Multiply this mass by 20, this is going to bounce off of you, and you won't know much about it. It's not going to hit you with as much force. I had the, oh, there it is. The little empty plastic wiffle ball. If we're outside in the yard playing, you'd much rather me hit you with the wiffle ball than with the real baseball, right? So once again, why? Well, this has more mass. This has less mass. If I throw them both at exactly the same speed, let's say I throw this at you at 30 miles an hour, and I throw this at you at 30 miles an hour. This is going to hurt. This is going to feel like I pinched you, right? And the difference is mass. Mass times acceleration equals force. Okay? Think of it this way. I have some blocks here. I'll set them up. I have a green block, a red block, a green block, and a red block. Okay? Now, we're going to do a small demonstration using these. Here's the wiffle ball. Okay? Now, I'm just going to take my finger and I'm going to flick it towards the blocks. I want you to watch what happens. Make an observation. Okay, it kind of moved the first block. Let's give it a second shot. All right, hit it harder. Finally got him, right? Now, we're going to do the same demonstration, but this time, instead of using the wiffle ball, we're going to use the baseball. Now, watch this. I'm going to give it the smaller flick, just like I did the first time. And then we'll do the faster flick on the second one. Here's the smaller flick. Now notice, on the smaller flick, the first time we did the wiffle ball, it barely moved the first one, and then it didn't do anything else. Well, this time with the smaller flick, not only did we move the first one, we pushed it with enough force for it to hit the second one, and that still pushed it back, and it hit the third one. Well, Johnson, if you just did one finger and you flicked it softly, what was the difference between the two? Well, once again, the difference is mass. The more mass something has, multiplied by its acceleration, equals it having more force. If a golf cart was going 15 miles an hour and it hits you, it would hurt. But if a car is going 15 miles an hour and it hits you, it could put you in the hospital. And if a semi-truck is going 15 miles an hour and it hits you, it could put you in intensive care, right? Same speed for all of those, same acceleration. The difference is the mass. Multiply it by a larger number, you're going to get hit with much more force. A second flick with the finger, this time slightly more forceful. And there they all get pushed, right? And then the harder one. That's gone. Okay, so what we see there is force equals mass times acceleration. The heavier something is and the faster it goes, the more force it's going to hit you with. Gravity pulls on everything the same. Gravity's always trying to pull something to the larger mass. In our case, Earth. I want to close today with a small demonstration as we wrap up. Okay? First off, just know I miss you guys. I hope you're doing well. I hope to see you back at school. If not next week, then maybe I can see you back in January. This is a small pile of blocks. Now, I can thank Nolan for these. These are actually his blocks. I'm going to use them for a couple of things. First off, we're going to do a demonstration that shows both of these factors at work. I have 5 wooden blocks. This one has a crocodile on it. Ta-da! We have 5 wooden blocks stacked up. Okay? This is a wooden spoon. All right? Now, all I'm going to do is, and there they are, stacked up so you can see, I'm going to apply a force to these, and by doing this, I'm going to show you 2 of Newton's laws. Now remember, the first lesson I showed you was the law of inertia. An object at rest will stay at rest until acted upon by an external force. An object in motion will stay in motion until acted upon by an external force. And now we have Newton's second law. Force equals the mass times the acceleration. The amount of force you hit something with is equal to your mass multiplied by your acceleration. So I'm going to do both. Here we have 5 blocks that are at rest. And if I walked out of the kitchen and left them alone, they'd stay at rest. They wouldn't move, right? But I'm going to apply a force. I'm going to apply the force of my trusty wooden spoon, right? But I'm not going to apply it to the whole stack. I'm not turning this sideways and just smacking the stack. That would be too easy, right? I'm only going to apply the force to the very first block on the bottom. The other blocks on the stack are actually going to stay at rest. Well, they're not going to float there. Of course, once I hit this block out from the bottom, gravity is going to pull on the rest of the blocks, and they're going to, of course, start to come towards the earth because it has a larger mass. But this trusty table is going to stop them, right? 1, 2, and 3. Woo! Notice? So, once again, we have the blocks at rest, and then once nothing was there to support them, down they came. But I think we can actually do an even better job. If I'm more careful about what I do, and I don't try to explode blocks all over the kitchen, then I believe we can actually do a demonstration where we show that the blocks can stay at rest, right? Check this out. I'll take our blocks. We're going to stack them up. There we go. Okay. Now, we're going to show both Law 1 and Law 2. Law number 1, inertia. An object at rest will stay at rest unless acted upon by an external force. The external force in this case is going to be the handle of this spoon. The things at rest are these blocks. But we're also going to show Newton's second law, that the force we apply is equal to the mass multiplied by the acceleration. Okay? And 1, 2, and 3. Notice once again, straight down with the other two blocks. Here we go. Notice that? Yeah. Fantastic to have you here today. I would like to see your demonstrations at home. Law number 1, Newton's first law, inertia. An object at rest will stay at rest. An object in motion will stay in motion unless acted upon by an equal or opposite force. Right? So, law 2, force equals the mass times the acceleration. An object's force is equal to its mass multiplied by its acceleration. Please wear your seatbelts. You are moving at the same speed as the car. If you're in a bus, you don't have belts in the bus, right? If the bus driver is traveling at 55 miles per hour, your body is traveling at 55 miles per hour. If you've ever been in a vehicle that had to all of a sudden get on the brakes and you felt pushed forward, I hope it's because you had your seatbelt on. That seatbelt helps you to decelerate, slow down, okay, at the same speed of the vehicle. Now remember, scientific language. No longer will we say speed up, slow down. What we will actually say is accelerate and decelerate. Accelerate means to speed up. Decelerate means to slow down. Fantastic to see you all. If you want to do your own demonstrations at home, I would love to get your videos or pictures. Send them to me, and I'll be coming back very soon with a lesson over Newton's third law of action and reaction. I hope you have a great day.